Welcome back to G Fun Facts Online. Today we are diving into one of the most fascinating engineering paradoxes in the modern world. If you picture the skyline of Hong Kong, you probably imagine a testament to hyper-modernity. You see glass and steel monoliths piercing the clouds, creating one of the densest and most futuristic urban jungles on Earth. But if you zoom in, if you look closely at the construction sites where these giants are born, you will witness a scene that seems to defy the logic of modern engineering. Clinging to the sides of gleaming 80-story skyscrapers are not the rigid, prefabricated steel tubes you would see in London or New York. Instead, you see an organic, chaotic-looking web of green bamboo poles. This is the story of bamboo versus steel. It is a battle of materials where ancient tradition does not just survive. It actually outcompetes modern technology. In this episode, we are going to explore the engineering marvel of Asian bamboo scaffolding, delving deep into the physics, the culture, and the sheer audacity of building the future with grass. To understand why a material as primitive-looking as bamboo is still used to wrap high-rise towers, we have to look past the aesthetics and put this material under the microscope. The first thing to realize is that bamboo is not wood. It is a grass. This is a crucial biological distinction because it gives bamboo structural properties that rival, and in some specific metrics even exceed, industrial steel. In material science, we often talk about whether a material is isotropic or anisotropic. Steel is isotropic. That means it has the same properties in all directions. It does not matter how you hold a piece of steel. It behaves the same way. Bamboo, however, is anisotropic. It is designed by nature to do exactly one thing perfectly: to grow tall and to resist the wind. This natural evolution has created a masterclass in structural efficiency. Let's look at the anatomy of the bamboo stalk, technically known as the culm. It is hollow. In engineering terms, a hollow cylinder is incredibly efficient because it maximizes the moment of inertia. It resists bending forces while keeping the weight to an absolute minimum. But nature takes it a step further. If you cross-section a piece of bamboo, you see vascular bundles. These are the fibers that give it strength. These bundles are not evenly distributed. They are most dense near the outer skin of the stalk. This is brilliant because when a pole bends, the mechanical stress is highest at the perimeter, the outer edge. Bamboo puts its strongest material exactly where the stress is highest. This is a natural optimization that human engineers try to mimic with I-beams and hollow tubes, but bamboo grows that way naturally. Then you have the nodes. These are the horizontal rings that punctuate the stalk. You might think they are just cosmetic or joints, but they act as natural stiffeners. When you bend a thin-walled tube, the danger is that it will buckle, meaning the walls collapse inward like a crushed soda can. The nodes prevents this. They stop the hollow tube from buckling, addressing a common failure mode found in thin-walled steel pipes. Now, let's talk numbers, because this is where the primitive grass really holds its own against the industrial giant. We compare materials using tensile strength, which is the resistance to being pulled apart. Bamboo has a tensile strength of roughly 28,000 pounds per square inch. For context, mild steel is often rated around 23,000 psi. That means, by weight, bamboo is actually stronger than steel in tension. While steel does win in pure compression, bamboo's compressive strength is comparable to concrete. But the real killer application here is weight. Bamboo is incredibly light. Moving a steel pole requires a crane or heavy lifting equipment. A bamboo pole can be carried by a single worker, often with just one hand. This completely changes the logistics of a construction site. You do not need heavy machinery just to get the scaffolding in place. But not just any bamboo will do. In the Hong Kong scaffolding trade, they rely on two specific species sourced from the Guangxi and Guangdong provinces of mainland China. First, you have the workhorses, known as cow jue or Bambusa praevariabilis. These are thinner and more abundant, used for the horizontal and vertical grid. Then, you have the heavy lifters, known as Mao jue or Philostachys pubescens. These are thick, robust poles, at least 75 millimeters in diameter. These are used for the critical load-bearing standards and the diagonal bracing that keeps the structure rigid. This brings us to the architecture of the scaffold itself. A bamboo scaffold is not a random collection of sticks. It is a highly sophisticated, three-dimensional truss system. It relies on flexibility rather than rigidity to survive the immense forces of wind and gravity. In modern high-rise construction, the standard is the double-layer scaffold. The outer layer is the safety web, holding the protective nylon mesh to catch falling debris. The inner layer, located about 200 to 250 millimeters from the building face, is used by workers to access the wall for tiling, painting, or window installation. Between these two layers, wooden planks are laid down to create walkways. The structural integrity of this system comes from a repetitive grid pattern described by Cantonese terminology that every sifu or master knows by heart. You have the zam or needle. These are the vertical standards that transfer the weight of the scaffold down to the ground or the transfer brackets. Then you have the hin or thread. These are the horizontal ledgers that tie the verticals together and provide lateral support. But the most crucial element for stability is the cheong or spear. These are the diagonal braces. In structural engineering, triangles are the strongest shape. Without diagonals, a square grid is unstable. It can easily tilt into a parallelogram and collapse. The cheong triangulates the structure, locking it into a rigid form. Now, here is where the philosophy of bamboo differs from steel. Steel scaffolding is rigid. If a typhoon hits a steel scaffold, the structure fights the wind. It stands its ground. But if the force exceeds the steel's yield point, it buckles and fails catastrophically. Bamboo scaffolding is compliant. When a typhoon slams into Hong Kong, the bamboo scaffold dances. It bends. It absorbs the energy and flexes. This ductility allows it to survive wind loads that might shear a rigid metal bolt. It is the engineering principle of the willow tree versus the oak tree. The willow survives the storm because it bends. The oak breaks because it resists. But how do you connect these poles? There are no bolts, screws, or clamps in a traditional bamboo scaffold. The entire structure, which can weigh tons and rise hundreds of feet, is held together by friction and knots. Historically, tough strips of bamboo skin were soaked in water and used as lashings. As they dried, they shrank, tightening the joint. Today, the industry standard has shifted to black nylon strips. They are rot-proof, UV-resistant, and have a known tensile strength. The scaffolders, known locally as spiders, use a specific repertoire of knots that can be tied in seconds, often with one hand while hanging 50 stories in the air. The foundational knot is the clove hitch, locally called the mancook. It is brilliant because it grips the pole tighter as the load increases. They also use the running knot for securing ends, and the complex pig cage knot to join multiple poles at a single intersection. The genius of the nylon lashing is that it allows for slight movement. A metal clamp crushes the fibers of the bamboo, creating a weak point where the tube could split. Nylon distributes the stress around the circumference of the pole, preserving the integrity of the hollow tube. So why does Hong Kong, one of the wealthiest cities in the world, use a poor man's material? The answer is ruthlessly capitalistic: speed and cost. Bamboo is cut to fit on site. If a steel scaffolder encounters a protruding balcony or an odd architectural angle, they need a specific prefabricated joint, or they have to wait for a custom part. A bamboo scaffolder simply takes out a machete, cuts the pole to length, and ties it. A skilled team can erect roughly 20,000 square feet of bamboo scaffolding in a single day. Dismantling is even faster. They simply cut the nuts and slide the poles down the center of the scaffold in a controlled free fall. Then there is the cost efficiency. A bamboo pole costs a fraction of a steel pipe. You do not need a fleet of heavy trucks to move it. A small lorry can carry enough bamboo to cover a house. And while steel lasts longer, bamboo is cheap enough to be semi-disposable. though good poles are reused 3 to 5 times. In the cutthroat world of Hong Kong real estate, where every day of delay costs millions, the agility of bamboo is unbeatable. But the engineering is only half the story. The execution is superhuman. The bamboo scaffolders of Hong Kong are a legendary breed of worker. It takes 3 years to become a licensed scaffolder. The training is a traditional apprenticeship. You start as an apprentice, spending the first year just passing poles and tying basic knots on the ground. You then graduate to a junior, allowed to work on the lower levels and learn the geometry of the grid. Finally, you become a sifu, or master. The sifu is an engineer-architect who does not work from blueprints. They look at the building, visualize the load paths, and direct the structure from experience. They feel the structure. This trade is steeped in tradition. Scaffolders worship Luban, the patron saint of builders and carpenters. Before a major project begins, a roast pig is often offered to the spirits to ensure safety. It is a unique blend of pragmatic engineering and spiritual reverence. And make no mistake, it is dangerous. Spiders work at extreme heights, often with minimal fall protection compared to Western standards, though regulations are tightening. They rely on their agility, balance, and the strength of their knots. The industry is seeing a decline partly because the younger generation is refusing to take on such a grueling and high-risk profession. So, is bamboo scaffolding doomed? The government of Hong Kong has begun incentivizing the use of metal scaffolding for safety reasons, and the code of practice for bamboo scaffolding safety becomes stricter every year. However, bamboo has found a new argument for its survival: sustainability. Steel production is a massive carbon emitter. Bamboo is a carbon sink. It grows to maturity in just 3 to 5 years, absorbing carbon dioxide the entire time. A bamboo scaffold is, effectively, a carbon-negative structure. At the end of its life, bamboo is biodegradable, whereas steel requires energy-intensive recycling. As the world turns toward green architecture, the ancient methods of Asia are being re-evaluated not as relics of the past, but as blueprints for a sustainable future. Bamboo scaffolding is more than just a construction technique. It is a symbol of Asian resilience and ingenuity. It represents a philosophy that values flexibility over rigidity, adaptation over domination, and harmony with nature over industrial brute force. When you look at a Hong Kong skyscraper wrapped in its green cocoon, you are looking at a masterpiece of engineering, where the organic and the synthetic meet. It is a reminder that sometimes, the best way to reach the sky is to grow there. Thanks for listening to G Fun Facts Online.